of x squared look like? A parabola. Okay, nice curve, both ends pointing up. X cubed is a polynomial. What did that one look like? The chair, right? So we are going to extend that and graph all polynomials in this chapter. So we'll have to have several different techniques to do that. Today we're going to talk about just some terminology things and some basic attributes of these graphs. So first of all, if I say polynomial, you have to know what I'm talking about. I told you x squared is a polynomial, x cubed is a polynomial. If you look in like Math Excel when you're doing a problem and it tells you the definition of a polynomial, they're going to give you a really long thing that looks like this. And all that's telling me is a polynomial is a bunch of powers of x added together. Okay, the powers of x, this is written where they are decreasing. The a's in front are just coefficients. So when you look at this, one big thing to note is all exponents are whole numbers. What are whole numbers? Not fractions, not negatives. It's just 0, 1, 2, 3. Those are our whole numbers. So when we're looking at polynomial, all of our exponents are nice. The degree of a polynomial is the highest power. In this case, with the definition I wrote, it would be n. N was the biggest exponent that I wrote down. What are coefficients? If I said 5x to the third, what's the coefficient? 5. It's the number out in front. So coefficients are just the numbers multiplied with x. So it's all those a's. A sub n, a sub n minus 1, and so forth. Just those numbers out in front. A constant is a number without a variable. Okay, so in our particular example up here, it's that last one, the a sub 0. There was no x with that. The leading coefficient is the coefficient of the term with the highest power. So when looking up here, we have x to the n power. That was our biggest power, so our leading coefficient is a sub n. It doesn't necessarily have to be the first one. Things don't have to be written in decreasing order. A lot of times they are, but you should check. And the leading term is the entire term with the highest power. So remember, terms are separated with addition and subtraction. So it's that whole thing, the coefficient and the variable together. Right, so this isn't necessarily something like on a test. I'm not going to give you a vocab section and ask you to write these definitions. But when we talk about polynomials, we're going to figure out that their graph is really based off the degree. And that leading term is going to tell us a lot about what the graph will look like. So we need to be able to pick that out. So when I say degree, you need to know we're looking for the highest exponent that we see. That term with the highest exponent becomes our leading term. When you draw a graph of a polynomial, if we think about the ones we know so far, x squared, x cubed, they're nice curves. So there's no sharp corners. It's not like an absolute value. It's not a V. So they're nice, smooth, continuous curves. There's no breaks in those graphs. Any transformation rules that we know are still the same. Those don't change. So first, I just want to look at a lot of different expressions. I want to decide if they're a polynomial. If they are, we're going to give the degree. If they're not, we're going to tell why not. So would A be a polynomial? Yes, it is. My degree, that's the highest exponent. What is my degree? 4. All right. B, a square root of x. A square root is like what power? It's the 1/2 power. I told you in a polynomial, all of your exponents are whole numbers. 0, 1, 2, 3, 4. So is this a polynomial? No. The reason is a fraction in the exponent. And what do you think about C? Would that one be a polynomial? Our definition said we are adding or subtracting powers of x. So can we divide them? No, there's nothing that allows that. Another way to think about it, if a variable is on the bottom of a fraction, it's like a negative exponent, so that's not allowed. So C is not a polynomial because we could say a variable in the denominator. Can't divide by a variable in a polynomial. D, f of x equals 0. Okay, do I have a variable in the denominator? No. Do we have any fraction or negative exponents? No, so it is a polynomial. The degree on this one is a little bit tricky though. 0 is kind of a special case. Degree is like saying how many variables do we have, okay? Would you guys agree that 0 is the same thing as saying 0x? Okay, and that would be a degree of 1, right? X to the first. But isn't 0 also the same as 0x squared and 0x cubed and 0x to the 4th? So can you tell me how many variables are with that? No. So this one is a special case. We just say it's no degree. We can't say. Because you could put any power of x with that. And the only case that happens is when it's just equal to 0. All right. G of x equals 8. Do we have any fraction or negative exponents? No, so it's a polynomial. Our degree. Is 8 the same thing as 8x? No. What power does that x have to go away? Because anything to the 0 power becomes 1. If it's just a number, the degree is like saying how many variables. Well, 8, how many variables are with that? 9. So, if it's equal to a constant except for 0, your degree is always 0. There are no variables there. And the last one. Okay, it's written differently. But could we choose to multiply this all out? Yes. When we do that, will we have any fractions or negative exponents? No. So this one is a polynomial. Your degree is like saying, if we multiply this all out, how many x's would we get? So we have to think, if I multiplied it, now we could take the time to actually do it, or we could reason through it. We have 3 x's here, and x squared here. So if you multiply that all out all together, 3 x's and 2 x's, how many x's does that give us? 5. Okay, so we're really just caring about what that highest exponent would be. So we have 3 here and 2 here, so altogether the highest power would be 5. And we will definitely be practicing a lot more of those. So if you're not quite sure on that yet, throughout the chapter, we'll be looking at those. Are there any questions so far? What I want you to do next, you can use a graphing calculator if you would like. I put 4 different basic polynomials on here. X cubed, x to the 5th, x to the 4th, x to the 6th. I want you guys to graph those. Draw me a rough sketch. So if you need to use a graphing calculator, that's fine. I just want you to take a minute and draw me a rough sketch of what each of those looks like. Okay, so x cubed, we probably knew that one without the graphing calculator. What does it look like? Chair. What does x to the 5th look like? Same thing. It's a little bit skinnier, but pretty much the same. What do you think x to the 7th would look like? A little bit skinnier, but basically the same. What does x to the 4th look like? Okay, basically like an x squared. What's x to the 4th look like? Or sorry, x to the 6th. Same thing, just a little skinnier. So how do we know if it's going to look like a chair or a parabola? Even or odd. So it turns out the graph of a polynomial is really determined by that leading term. Okay, a polynomial will have other things added onto it, which will change the graph slightly. But the big picture, how the ends are going, is determined by that leading term. So it resembles x squared if the power is even, and x cubed when the power is odd. And as that exponent gets larger, we said the graph gets skinnier, so I'm just going to say the graph narrows. So the higher the exponent, the skinnier the graph. But overall, it follows a basic shape. That's what's called the end behavior of a graph. So that is one of the main things we are talking about today. End behavior is what happens as your power gets really big in a positive or negative direction. So it is determined solely by the leading term. So the leading term is the term with the highest power. And there are 2 different cases if it has an even or an odd degree. So when our leading term has an even degree, we have 2 options. If it's a positive, it's like a basic x squared. So I'm just going to draw 2 arrows. When I ask you end behavior, you can just draw arrows for me, telling me what direction it's going. What happens if I put a negative in front? If I say negative x squared, what happens to your graph? It reflects across the x-axis, so both ends end up pointing down. So if the power is even and the coefficient is positive, both ends are going up. If that coefficient is negative, both ends go down. If we have odd degree, we said anything with an odd degree will look like an x cubed. So a basic chair, the left end is pointing down, the right one is pointing up. But if I said negative x cubed, what happens? are other ways of saying this. If you were to look in a textbook, they're probably not just going to draw arrows. They're going to say something as x approaches negative infinity, f of x approaches positive infinity. As the x is going to the negative direction, the graph is going up. And as x is going in the positive direction, the graph is going up. I find that just to be more effort than is needed. So don't be overwhelmed if you see something like this. But all I'm expecting, anytime I ask you for end behavior, I just want you to draw me two arrows. Tell me which way the ends are pointing. Okay, that's all I need from you. So let's practice. We're just going to look at some some equations and see if we can determine what the end behavior would be. So if I'm looking at this, the only thing you are worried about is that leading term, the term with the highest power. So when I see a 4x cubed, x cubed tells me it looks like a chair. It's a positive coefficient, so it doesn't change. So my end behavior, this end's going down, this end's going up. What is the leading term on this one? Okay, so x to the 6th, what does that tell me? Right. Looks like a parabola, and the negative in front makes them both point down. So our end behavior is down, down. All right. This one is written in factored form. When we are talking about our graphs, for the end behavior, we need it to be multiplied out, but do we care about the entire polynomial when it's multiplied out? No, only that leading term. So what I do, I don't actually multiply everything out. I just kind of shortcut it. We have a 3, the highest power of x in this parenthesis is x. In this one we have an x, but it's going to be squared. So if you take 3 times x squared, you get 3x cubed. So if we were to multiply it out loud, my leading term would be 3x cubed. What does that tell me my end behavior would be? It looks like a chair. Odd powers, so if this exponent is odd, your ends are going opposite direction like a chair. It's a positive 3, so it doesn't flip. Last one. Again, I don't need everything. I just need to figure out what my leading term would be. So we have a 1/2. In this parenthesis, we would get an x squared. In this parenthesis, if you have x squared cubed, what do you do with those exponents? So that's an x to the 6th. This one we have an x to the 4th. So if you multiply that all out, we get 1/2 x to the 12. Okay. The fact that my exponent is even tells me what? Looks like a parabola. Then we check. The 1/2 is positive, so it doesn't flip. So it's a normal parabola. Up, up. Questions on those? I would like for you to take a second and try the next one without using your graphing calculator. So just using what you know about end behavior, try to match the equation with the graph for each of these. So if I look at graph A, both ends are pointing down, so that means it has to be an even exponent and a negative coefficient. So that would be G. Okay, these ends are going opposite direction, so it's an odd power. But it's like a normal cube, so a positive coefficient. So which one is that? Okay, both ends are pointing up, so it's an even power, positive coefficient, so that would be F. This one, ends are going opposite direction, so it's a negative, so it's an odd power. but it's flipped, so a negative coefficient. So that would be this one. How do we do on this? Let's talk about a few more things to wrap up. When I mentioned turning points, that's just where the graph changes direction. So it could be like our graph was increasing and it switches to decreasing. This is a turning point. Or the graph could be falling and it switches to rising. That's a turning point. Those are also sometimes called extrema. Extrema just means max and min points. So when your graph changes direction, you are creating a high or low point on that graph. There's two different kinds of maxes and mins. The first one is absolute, which is the highest or lowest on the entire graph. These can be endpoints. And a local max or min is just higher or lower than surrounding points, not necessarily on the entire graph. Those don't include endpoints because endpoints don't have things on both sides. So we'll take a look at a picture and kind of identify those maxes and mins so you can see the difference in the two types. Okay, so when I'm looking at this one, all right, so that first graph, point 1, when I did a different example. Let's just go to this one. Okay, so if I want you to tell me the local extreme, that means the local maxes and mins of graph F. So here's F. Local means it can't be an endpoint, which, do we have any maxes or mins at the endpoints? No, both ends are going up, so there isn't one there anyway. What would be my local max? That means a point that's not necessarily the highest on the entire graph, but just higher than the surrounding points. CD. What about local min? Doesn't have to be the lowest on the entire graph, but lower than the things around it. So that would be AB is one. There is another one. EH also counts as a local. Okay, AB, it's not the lowest on the whole thing, but it's lower than the points on both sides. Same thing with EH. Okay, if I'm looking at G, what would be my local max? MN. What about local min? Okay. Absolute max or min. be higher or lower than the entire graph? Does graph F have an absolute max, a point that is higher than everything else? No, these ends keep going up, so there will be no local max, or absolute max, sorry. Is there an absolute min? Is there a point that is lower than everything else on the graph? EH. So EH counts as both a local and an absolute. You don't have to have absolute maxes and mins. A lot of times polynomials do not. When I'm looking at G, does it have an absolute max? No, because this end's going up forever, so there is no highest point. Is there an absolute min? No, this one's going down forever, so there is no lowest point. So no max or min for that one. Okay, so local is just highest or lowest in that area. Absolute is the entire graph. Any questions there? Okay, I'm going to stop in just like 2 minutes. Just want to talk about a couple things that we'll pick up with tomorrow. These turning points are actually related to the degree. When you are looking at the degree, you can have at most 1 fewer turning points. So for instance, if my degree is 10, how many turning points could I have? 1 less. So it would be 9 turning points. Now at most, it doesn't have to have 9, but it could. If I said my degree was 7, how many times could it change direction? 6. So it's always 1 less. And it works in reverse. If you're looking at a graph and it changed direction 4 times, your degree would have to be at least 5. Okay? So that's really what this is saying. Second thing I want to talk about, x-intercepts. That's your solutions. It's how many times your graph hits the x-axis. And it's always up to the degree. Okay, I say up to because it doesn't have to be exactly that, but x squared, it could hit the x-axis at most 2 times. Is it possible to have an x squared that just hits the x-axis once? Yes. Is it possible for it to never hit? Yeah. So if I said x cubed, at most, how many times could it touch the x-axis? 3 times. X cubed could hit the x-axis 3 times. If I said x to the 7th, how many times could it touch the x-axis? 7 times. Okay, so the x-intercept is the same as the degree. Turning points is 1 less than the degree. All right. I'm going to go ahead and mention this last one, and we're going to look at some of examples with it tomorrow, but we'll go ahead and just get it down in our notes, and then we'll talk about why. So the last thing that we're going to look at when we're talking about our polynomials is the multiplicity. Up until now, I've told you to write down multiplicity because it will matter later on, and the graph is when it comes into play. So it turns out if the multiplicity is odd, the graph will always go through our x-intercept. So if this has an odd multiplicity, the graph's just going to hit it and go through. But when it has an even multiplicity, what will happen is we'll hit it and bounce off. So if we think about x squared, okay, your basic x squared graph, y equals x squared. It hits at 0 and it bounces, right? Because that 0 has a multiplicity of 2. This is the piece that we'll be talking about tomorrow and looking at a little bit more. So, at this point, we are stopping for today. There is a handout posted on Google Classroom. What I want you to do is 1 through 18. I want you to skip the last 2 questions. we are going to start class tomorrow by doing those two together, talking a little bit more about the graphs. But this handout, it is not meant to be anything too time consuming. So pull up Google Classroom and let's take a look at our directions. One through 8 are saying, tell me the end behavior. When I ask for end behavior, what am I asking you to do? Draw 2 arrows. So number 1, what's my end behavior going to be? Down, up. It's an x cubed, positive. So that's all you're doing on 1 through 8 is drawing those arrows. Number 9, it says state the maximum number of turning points. What did we say about turning points? 1 less than the degree. So number 9, what's our degree? 5. So how many turning points can it have? 4. Okay, so the next 4, you're just writing a number. Then once you get to problem 13, you're answering some questions based off those graphs. Right, so you should have time to get this done.